Bismillahirrahmanirrahim. Dear students, welcome to the. So far, we have discussed the topic which are highlighted in this window of to directivity, and in today's lecture we will discuss the numerical techniques, antenna efficiency and gain, and some other topics. First of all, let us start with the directional pattern. Okay, directional pattern is that pattern which has more directivity in some direction and very less directivity in other direction. For example, if you take this example as an example, the radiation intensity, which is given by u, theta and phi, equal to b naught cos theta and theta, and this is within this angular span. Theta varies from 0 to 90 degrees and phi varies from 0 to 25 radians. This pattern is directional, and the more it will be directional if the higher is the order of the cosine. That is n, if n is equal to 0, then cos of raised to the power 0 will be 1. So the pattern will be non-directional. It will be isotropic in that case, and the pattern will be equal to b naught only. Now, when n is equal to 1, it will be equal to b naught cos of theta. It will become slightly directional. When n is equal to 2, it will become b naught cos square theta. It will be more directional as compared to b naught cos theta and b naught. So as the order of the n increases, the directivity will increase accordingly. And for this pattern exists only in the half hemisphere, and it is 0 in the rest of the space. Here is an example of that pattern, that is the normalize. If we normalize the previous pattern by dividing both sides of the equation by b naught, so we get the radiation intensity equal to cos n theta. Okay, and as I said, it exists only in the half hemisphere. So you see this balloon type directional pattern exists only in the upper hemisphere, and it is 0 in the lower hemisphere. I will discuss where it is necessary. However, those slides which does not need too much discussion, I will briefly go through those slides. So far, as in the previous lecture, for directional pattern, we can find the directivity, the maximum directivity, by using this formula 4 phi divided by omega A, where omega A is the beam solid angle, right? And that beam solid angle can be calculated by the exact equation as shown the first, the green equation, or it can be calculated by using the Krauss formula or the Thai and Pereira formula. Okay, but for that, what is required, that we should know the half power beam width in the one plane and the other plane, and both planes are perpendicular to each other. Now once we know the beam solid angle, so we just divide 4 pi by beam solid angle and we get the maximum directivity d naught. So this is the formula for the maximum directivity. Okay. Now let us come to omnidirectional pattern. What is omnidirectional pattern? Omnidirectional pattern is that pattern for which the directivity or gain in one plane is omni, that is equal in all direction. However, in the orthogonal plane, the pattern is not omni, it is directional. And the general mathematical form of that omnidirectional pattern is sine pattern. The numerical pattern will be equal to sine theta, sine square theta, sine cube theta, etc. So that will be omnidirectional pattern. Mostly the omnidirectional antennas are dipoles, monopoles. These are omnidirectional antennas. Here is the general pattern for the omnidirectional antenna. So here omnidirectional pattern with minor lobes is shown. So that is the main pattern. You see the horizontal that is the donut shape pattern. However, some minor lobes are also shown here, which are very minor, has less power as compared to the main lobe. The general pattern is of the order of n sine n theta. Again, theta varies from 0 to phi, and phi varies from 0 to 2 phi for the omnidirectional pattern. So you see here, as the order of the n increases, the directivity in the one direction will increase. Okay? So the omnidirectional pattern will become more directive if the order of the n increases. It has already been shown with examples in the previous lectures that for the infinitesimal dipole, the pattern was equal to sine square theta. Okay, and for that the directivity was calculated, which was equal of somehow 1.7 dBs, and the pattern for the half wavelength dipole was sine cube theta, which is slightly more directive as compared to sine square theta, and for the half wavelength dipole the directivity was somewhat 2.3 dB. So as the order of the n increases, so the directivity of the omnidirectional pattern will also increase. This is the same pattern, but with no minor lobe shown here. Now, so the directivity for the omnidirectional pattern can also be calculated by using approximate methods as well as the exact methods. Exact method has already been explained, that we need to calculate the beam solid angle or the total radiated power, and then we use the formula for the directivity to find that directivity. However, if we know the half power beam width of that omnidirectional pattern, sine theta and theta, so we can use McDonald method or Posar method to find the maximum directivity by putting the values of the half power beam width in either of the equation. Now this graph shows summary of the McDonald, Posar, and the exact directivity for the omnidirectional pattern, which is u is equal to sine n theta. On the vertical axis to the left, the directivity, maximum directivity, is shown as a dimensionless quantity, and the right hand vertical is the same directivity but in dBs. On the horizontal axis, we have n, which is the order of the sine function, and it varies from 0 to 450. Similarly, we have half power beam width also shown here, and it varies from 180 degrees to 6.4 on the right hand side. We see here that the approximate method of McDonald and Posar's, they give nearly similar results as that of the exact equation. Exact equation is the solid line, right? And the approximate methods of McDonald and Posar gives more accurate results for lower values of n, and slight deviation for higher value of n. Okay. As the order of the sine theta increases, so the deviation between the exact and the approximate method slightly increases. Also, we see that as the from this graph we can see that as the order of the sine function increases, so is the directivity increasing. You see, so as the directivity increases, so in other words, it means that the half power beamwidth should reduce for directive methods, as it is obvious here. So as the directivity increases to the right, we see that the half power beamwidth reduces to 6.4 from 180 degrees to 6.4. So they are inversely proportional. Directivity is inversely proportional to the beam solid angle, and beam solid angle is directly dependent on the half power beamwidth. So from the previous figure, that figure can be used for design purposes as follows. First, specify the desired directivity and determine the value of n and half power beamwidth of the omnidirectional antenna pattern. So if we know the directivity and the order of the pattern is unknown, or the half power beamwidth, so from the directivity we can extrapolate the value of n and half power beamwidth. Second, specify the desired value of n or half power beamwidth on the horizontal axis, and determine the directivity of the omnidirectional antenna. If we know n or half power beamwidth, so we can extrapolate that to the directivity curve and we will get the value of directivity. To demonstrate the procedure, an example is taken. Example 2.8, which is also given in the book. Here, design an antenna with omnidirectional amplitude pattern with a half power beamwidth theta is equal to, that is half power beamwidth is equal to 90 degrees. So that means that the angle at which the half power points will occur will be equal to 90 divided by 2. That means 45 degrees. Theta h will be equal to 45 degrees. Express its radiation intensity by U is equal to sine n theta. So since this is a omnidirectional pattern, so it will be a sine pattern. However, an n is unknown here. Determine the value of n and attempt to identify the element that exhibits such a pattern. It means that determine the value of n and also find which type of antenna it is. Also determine the directivity of the antenna using the exact method and the approximate methods of McDonald's and Poisson. Now, data is given. It is a half data, the only data that is available, that this is omnidirectional antenna with a half power beamwidth of 90 degrees. So, since the half power beamwidth, come to the solution, since the half power beamwidth is 90 degrees, the angle at which the half power point occur is theta h is equal to 45 degrees. Half power point means that at that point the value of radiation intensity will become equal to 0.5. Okay, so putting the values, 0.5 is equal to sine n 45 degrees, which is equal to 0.707 raised to the power n. Now if we solve this equation for n, we can get the value of n, which is equal to 2. So it means the radiation intensity of the omnidirectional antenna is U is equal to sine square theta, and this is the radiation pattern of the infinitesimal dipole or a small circular loop antenna, which will be discussed in chapter 4 and 5 respectively. Next step is to find the directivity using the exact formula. So the exact formula has already been used for this type of antenna, and we have calculated that the maximum radiation intensity Umax will be 1, which will occur at theta is equal to 90 degrees. Total radiated power was also calculated, and it is equal to 85 divided by 3. Now putting the values in the directivity formula, so we got 3.2, which is 1.5, or on in dB scale it is 1.761 dB. Since the half power beamwidth is equal to 90 degrees, so the exact solution gives us the directivity of 1.761. Okay. Since the half power beamwidth is 90 degree, which is given, now we can use the Poisson formula or the McDonald formula given in equation 2.33a and 2.33b respectively. So the one method, the Poisson method, will give us an approximate maximum directivity of 1.71, which is nearly equal to the exact solution. Okay, very close to the exact solution. Or if we use the other formula, Poisson formula, so it will give us a directivity of 1.807, which is also close to the exact solution. It's slightly greater than the exact directivity, and in this case, in the McDonald case, the directivity is slightly less than the exact solution. Thus the value of n and the three values of the directivity can also be obtained directly from the figure 2.18. Okay, as I said, that graph can be used for finding the value of directivity and n if we know the half power beamwidth. Now let us start some numerical techniques. Numerical techniques can also be used to find the directivity of antennas. Like exact methods, we have exact solutions. We also have some approximate methods for omnidirectional and directional pattern. However, those approximate methods are only applicable either to directional pattern or omnidirectional pattern. But if there are some complex pattern which does not lie exactly within those two classes, then we can use numerical techniques to find the directivity of antennas. We can say that there are two types of variables. One is the separable variable and the other is the non-separable variable. Here it is very important. If the radiation pattern, which is U is basically radiation intensity pattern, if it is a separable function, that means the theta function and the phi function can be separated from each other, as an example, equal to sine theta and sine square phi. So this can be easily integrated. Okay, integral is possible, easily possible, and that integral, that is basically total radiated power integral. So you can easily find the total radiated power, and then you can find the directivity by using the directivity formula. However, if this function is non-separable, so the integral will become more difficult, and in that case the exact solution will be very time consuming. Okay, and sometimes it will be impossible. So in that case we will use the numerical methods to solve that problem. Here you see that the radiation intensity, if it is a function of theta and phi, a separable function, first of all, let us do it for a separable function. So B naught f theta g phi, where B naught is a constant, that is the maximum radiation intensity for a given value of theta and phi. F of theta is some function of theta such as sine theta, cos theta, etc. G of phi will be a function of phi, which is like sine phi, sine square phi, or cos square phi, or any other trigonometric or function, any function of phi. Now we know the formula for the maximum directivity, which is 4 phi u max divided by p rad, or it is also equal to 4 phi divided by beam solid angle omega a. So we can find u max, the maximum radiation intensity, like this, which is equal to the value of u at some coordinates theta max and phi max. Now the total radiated power can be calculated by the closed integral as discussed previously. It is equal to u d omega. If we use that formula, it is equal to u d omega. D omega is the differential, the differential solid angle, which is equal to sine theta d theta and d phi. So total radiated power will be like this. Okay. Now we can separate, as it is a separable function, so we can separate the theta integral and the phi integral. Okay, as shown here, the blue integral is the phi integral and the green integral is the theta integral. Two variables, that is theta and phi. Okay, and the limits of the integration are also given. Okay. So by exact method we can find the total radiated power while solving the integral in equation 2.37. Okay. So the theta integral can be approximated to a summation, a numerical summation, that is equal to h theta. H theta is basically this function, f theta into sine theta, the product of two theta functions. So it can be a summation I start from 1 to n h theta I and del theta I. Okay, or it can also be written like this by putting the values of h theta. Now what is del theta I? Del theta I is the step size of the theta. Okay, so there are n, we are basically dividing the theta plane into n samples. We take n samples along the theta plane. So similarly the other integral, the phi integral, can be approximated to a summation j start from 1 to m and g phi j del phi j. Okay, and del phi is the differential or step size of the in the phi plane. Okay, we divide the phi plane into m samples. So if we take total of m by n samples, we can sample the whole radiation pattern of the antenna, and then we can calculate the total radiated power by adding the contribution from each plane. Okay, now two methods can be used. One is the trailing edge method and the other is the midpoint method. Both will give the same results, but however the first one, the trailing edge method, is more easy to imply as compared to the midpoint. So what is the value of theta I and phi j? If you have studied the numerical analysis subject, so you can easily find it. Theta I will be equal to I into phi by n, where I starts from 1 to n. Phi j will be equal to j into 2 phi by m, where j starts from 1 to m. So if, let's say for example, we take 10 samples. Okay, so we take 10 samples along theta planes, and we take 20 samples along the phi plane. So in that case, if the radiation pattern is not separable, so in that case also, if it is not separable, then the exact solution, as we see on the top of this slide, the first equation on the top of the slide, is not easily attainable. So in that case also, the numerical technique can be used. So if it is not exactly separable function, u is not a function of which can be separated into theta and phi components, then this integral, which is the exact integral, can be approximated by this summation. Okay, so b naught 2 phi by m to phi by n, and j start from 1 to m, and I start from 1 to n, f theta I. So it's a double for loop applied to that function, radiation intensity, and it calculates the total radiated power using the numerical method. Okay, here is example 2.9. So in this example 2.9, radiation pattern is given, which is equal to b naught sine theta and sine square phi, shown here. Limits of integration are also given. Theta varies from 0 to phi and phi varies from 0 to phi. Elsewhere the pattern is 0, so the pattern exists only in the right hemisphere, as you see here. Okay, that color pattern is shown. The maximum value of the pattern will occur at theta is equal to 90 and phi is equal to, if both the coordinates are 90. So in that case, the maximum pattern will be equal to b naught. Okay. Now, if we use the trailing edge method and take m is equal to n is equal to 18 samples, okay, so the step size, the angle step size along the theta coordinates and phi coordinates will be the same, each equal to phi by 18. Okay, or in other words, 10 degrees. Okay, because phi is equal to 180 degrees, so del theta I is equal to del theta j is equal to 10 degrees. Now using a numerical equation for the total radiated power, so integration is replaced by summation, and the green integral for the phi integral, the green summation is for phi integral, and the pink one for the theta integral. Now both integral, because the functions are the same, sine square phi j and sine square theta I, so they will give the same results, you will see. So phi j, the angle at those points, j is equal to 1 to 18 samples along the phi plane, and I is equal to 1 to 18 samples across the theta plane. Now, so there will be 18 values of theta, and that will give us the total radiated power. Total radiated power will be calculated to be b naught phi square by 4. Okay, each summation give us 9, value of 9. Maximum radiation intensity, as I said, will occur at theta is equal to and phi is equal to 90, and it will be equal to B naught. Now using the formula of the directivity, which is equal to 4 phi u max divided by P ret, putting all the values, comes out to be 5.0929. And on dB scales, taking log on both sides, will give us 7.0697 dB. Now if we use the midpoint method, it will give again the same result as shown here. So the same result, 5.0929 by the midpoint method. So both methods gives the same value of directivity. And similarly, the maximum directivity can be calculated by the exact method. Okay, so we are total radiated power calculated by the exact method is given by this B naught 5 by 2 into 5 by 2, then 5 by 2. Both integral are the same, so they have the same value 5 by 2. Okay. Here the first integral, the limit for the first integral is 0 to 5, not 2 5. 2 5 here is a mistake in the slides. So it is from 0 to 5. Now, so you see that the numerical methods give almost the same accuracy as the exact method. So it can be simply programmed in a computer to find the directivity for any class of antenna for which the numerical pattern does exist. Is that pattern. Okay. Next topic is the antenna efficiency. Antenna efficiency basically is the total, the ratio of the output power, radiated power to the input power. And the input power is basically the sum of the output power plus some losses. Okay. Now the total antenna efficiency E naught, denoted by some, is used to take into account losses at the input terminals and within the structure of the antenna. So total efficiency considers two types of losses, that is the mismatch losses at the input terminal as well as the conduction losses within the structure of the antenna. So the input terminals, that is the losses are due to reflection because of the mismatch between the transmission line and the antenna. If the antenna is not matched to the feeding line, then there will be mismatch, standing waves, and the efficiency will slightly drop. Also, if the not good materials are used in the design, then there will be I square R losses, that is conduction and dielectric within the dielectric, and efficiency will suffer. This diagram basically shows the antenna reference terminals, that is the structure of the antenna. It is the transmission line, the feed line, okay, and then that the antenna structure. So there are input terminals and they are also called gain reference terminals, okay, and similarly output terminals, and those are called directivity reference terminals. Okay, the output terminal, you see at the output terminals, if we observe, we will only see the radiation pattern. Okay, so here we will only see the radiation pattern. Like there will be some radiation pattern like this, that is u theta and phi. So the directivity is completely dependent on the radiation pattern. Okay. However, if you see the gain reference terminal, so at the input terminals, the gain is dependent not only on the pattern, that is directivity, but also it is dependent on the reflection, okay, and the structure losses. So two terms will be considered while calculating the gain, that is the reflection here at the end, and also the losses. These are demonstrated here. So that is reflection, conduction and direct losses are shown here. So at the input terminal, if the antenna is not matched to the feed line, there will be reflection. R will not be equal to 0. So some power will be reflected back towards the sending end. And if the dielectrics is not perfect, or the metal conductors are not perfect, so antenna efficiency, the total efficiency, which is denoted by E naught, is the product of ER, EC and ED. EC and ED cannot be separated from each other because this is the efficiency due to conduction within the conductors, and that ED is the efficiency due to the dielectric, and they cannot be separated, so they are combined into one term, ECD. ECD is the radiation efficiency and ER is the reflection efficiency. Now the reflection efficiency is given by 1 minus Rn whole square. Okay. What is Rn? Rn is the reflection coefficient at the input of the antenna. So ECD is radiation efficiency, ER is reflection efficiency, E naught is equal to total efficiency. Okay. So take an example. Here is a transmission line and a load. Load in this case is an antenna. Okay. An antenna which has an input impedance Zn is equal to ZL, for example. That Zn is the load impedance, our antenna input impedance here. Transmission line has a characteristic impedance of Zc. So we can find the reflection coefficient at the input of this circuit, and it will be equal to ZL minus Zc divided by ZL plus Zc. Putting the value Zn minus Zc and Zn plus Zc. Zn is the input impedance of the antenna. So the reflection efficiency can be calculated if we know the value of reflection coefficient at the input, which is given here. Similarly, VSWR can also be, voltage standing wave ratio can also be calculated if we know the value of reflection coefficient. And similarly, if VSWR is known to us, we can find the value of the reflection coefficient. The next important term is the gain. What is gain? Gain is similar to directivity. However, as I explained, that directivity only takes into account only the pattern or the directive properties of the antenna. However, the gain takes into account the pattern as well as the losses due to the conduction and dielectric, and the losses at the input due to mismatch. So gain can never be greater than the directivity. However, the maximum gain can be equal to the maximum directivity. Usually gain is slightly less than the directivity because of those losses, because there is no perfect material in the world and there can be no perfect matching of the antenna to the field line. So that's why gain is equal to efficiency multiplied by the directivity. So the efficiency factor comes into account when we calculate the gain. Gain of an antenna in a given direction is defined as the ratio of the intensity in a given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically. The radiation intensity corresponding to the isotropic radiated power is equal to the power accepted, that is the input power by the antenna, and divided by 4 pi. Okay. So the input power, if it is equally divided, so that means we in the whole spherical coordinates, so we divide it by 4 5 solid angles. Gain of the antenna is closely related to the directivity. It is a measure that takes into account the efficiency of the antenna as well as its directional capabilities, that is directivity. However, directivity is a different thing. That is, directivity is a measure that describes only the directional properties of the antennas, and it is therefore controlled only by the radiation pattern. Here are, you see how the total radiated power is related to the input power. As I said, the output power is also equal to efficiency multiplied by the input power. Or you can also call the radiation efficiency is the ratio of radiated power to the input power. So that is the mathematical equation for the gain. Gain is denoted by the symbol G. Okay, maximum gain can be calculated, which is 4 phi to radiation intensity in a given direction, which is u theta phi, and the total input or total accepted power by the antenna, which is Pn. Now we know Pn is related to Prad by this equation 2.47, equation number 2.47. Prad is equal to ECD into Pn. From this we get the value of Pn, which is equal to Prad divided by ECD. Now substituting this Pn input power into equation 2.46. Okay, so we get this equation 2.48, which is 4 phi u divided by Prad divided by ECD. Okay, taking ECD out of the brackets, and the term within the bracket is basically directivity, which is previously discussed in detail. So we calculated, we found that the gain is dependent on the efficiency as well as directivity. It is a product of efficiency and directivity. Now the gain will be equal to directivity if the efficiency is 100%. If efficiency is 1, that is the radiation efficiency when there are no losses within the structure. So the gain, the E will be 1 and G will be equal to D. However, practically G will be slightly less than dA because nothing is lossless in this world. So gain can never be greater than the directivity, can be always less than the directivity. So the maximum gain is equal to ECD into maximum directivity D now, where ECD is the radiation efficiency, EC is the conduction efficiency, and ED is the dielectric efficiency, but both cannot be separately calculated. So that's why both are combined into a single factor, which is ECD or radiation efficiency. So in formulas, and then the gain can also be calculated in dBs. So what we take 10 log of 10 of that equation on both sides, so we get the maximum gain in dBs. Okay. So multiplication in logarithmic scale is equivalent to addition. Okay. So this is some addition in the logarithmic scale. Now that was the formula for the maximum gain, okay, without considering the losses at the input. However, the losses within the structure were only considered in the previous gain. But we know that there are also losses at the input if the antenna is not matched to the feed line. So in that case, we will not take the radiation efficiency, but how we will consider the total efficiency in that case. Okay, so that gain will be called absolute gain. So absolute gain is the product of the total efficiency multiplied by the directivity, and the total efficiency is equal to ER into ECD, where ER is the reflection efficiency, which is equal to 1 minus R n whole square. Rn is the reflection coefficient. Okay, so the absolute gain will be less than that previous relative gain, IEEE gain. So because of the reflection efficiency term included in this, because it takes two types of losses into account: reflection losses and losses within the structure. And the previous equation, it was only considering the conduction losses, it was not considering the mismatch loss. The next term, that is the relative gain, the ratio of the power gain in a given direction to the power gain of a reference antenna, that is a lossless isotropic source. This type of gain is called relative gain. The power input must be the same for both antennas. That is the condition, that the antenna for which the relative gain is supposed to be calculated. So input power for that antenna and the reference antenna, which is isotropic, for both the input power should be the same. Then we can calculate the relative gain by equation 2.46a. So gain is equal to 4 phi u theta phi divided by Pn lossless isotropic source. As discussed that the radiation pattern could have two components, theta component and phi component. So the directivity will have two components, d theta and d phi, called as partial directivities. So similarly, the gain could have also two components, g theta and g phi, and these are called the partial gains in the theta and the phi plane. So if we know the partial gains in the two planes, we can find the total gain of an antenna by adding the partial gains. Now here is an example, 2.10. A lossless resonant half wavelength dipole with input impedance of 73 ohm is connected to a transmission line whose characteristic impedance is 50 ohms. Assuming that the pattern of the antenna is given by U is equal to B naught sine cube theta, find the maximum realized gain of this antenna. Now, some data is given. First, it is a lossless resonant half wavelength dipole. Lossless means that material used in the design of the dipole antenna is perfect. So that means the ECD, the radiation efficiency, will be 1 or 100%. Half wavelength dipole, that means resonant means that the input impedance of the dipole will only have resistive component, and the reactive component of the input impedance of that dipole will be 0. That is a resonant dipole, resonant antenna. Half wavelength means its overall length will be equal to lambda by 2. Now for half wavelength dipole, the input impedance is also given, 73 ohm, and that is standard for a dipole antenna. 73 ohm is the input impedance of a dipole antenna. Now this dipole is connected to a transmission line whose characteristic impedance is 50 ohm. So if we draw it, it is like, it is that dipole antenna, and it is connected to a feed line like this. Now ZC, characteristic impedance of this feed line, is 50. Okay, 50 ohm, and this is that lambda by 2 dipole, lossless dipole, and the input impedance at the input terminals here, these are the input terminals. Here Zn will be equal to 73 ohm. Okay, it is a resonant dipole, that means Zn is equal to 73 plus minus j 0, that means no reactive component. It is a lossless, that means that ECD is equal to 1. Now the radiation pattern is given, this, which is equal to U is equal to B naught sine cube theta, and the gain of the antenna is unknown. Gain is unknown. So gain, what is gain? Gain is basically equal to total efficiency, maximum realized gain, E naught into directivity. Okay, and directivity can be calculated by four phi U max radiated power. Okay. Now total radiated power is basically the formula for that is given total and closed integral. Okay, which is solved on the next slide. So if we know the total efficiency, and total efficiency basically E naught can be calculated as ER into ECD. Okay. So Zn is equal to 73 ohm, Zc is equal to 50, lossless, so ECD is 1, U is given. Now using the formula, D naught is equal to 4 U max divided by P rate, we can find the relative gain. G naught is equal to E naught into D naught. Now for maximum directivity, we need to find the U max, the maximum radiation intensity, which will occur for this particular pattern at theta is equal to 90 degrees. Now using the formula for the total radiated power, which is equal to over the whole spherical coordinate system. So the value of theta varies from 0 to 5, and the value of phi coordinates vary from 0 to 2 pi. U is given, which is equal to B naught sine cube theta, and one sine theta is here, so sine cube theta into sine theta will become sine 4 theta. Now if we integrate this sine 4 theta, it will give us 3 phi by 8. So the total radiated power will become, similarly the phi integral will only give us 2 phi. Okay, phi integral is only dependent on d phi, so that will give you 2 phi. Now take it, will become B naught 3 phi square by 4 is the total radiated power. So we get the value of directivity by putting the values of power. 4 pi into B naught, this is U max, divided by total radiated power, simplify it, and we get a dimensionless quantity which is equal to 1.697, which is nearly 1.7, okay, for a dipole. And if we convert it into dB, it will be slightly greater than 2. Yes. Now the total gain can be calculated, the absolute, the maximum gain. Maximum gain can be calculated at the ECD into D naught. ECD is 1 because it is a lossless dipole. So 1 into 1.697, it gives us 1.9. That is some problem with the value basically. However, it gives us 1.967, which is 2.297. Yeah, 2.297 dB. Now the reflection efficiency can be calculated because the value of the characteristic impedance is different than the antenna input impedance. So there is a mismatch between the input impedance of the antenna and the line impedance. And that's why the reflection coefficient is not 1, not 0, but rather it is 0.187. Putting the values, we get the value of reflection efficiency, which is 1 minus square of 0.187. So 0.965, it is not 1 but less than 1. So that is due to that mismatch. Now due to this mismatch, the total efficiency will be not 1 but 0.965. So therefore the absolute gain will be less than the maximum gain, and that is 1.638 here. 1.638, which is 2.142 dB. So the absolute gain is slightly less than the maximum gain due to the because it takes both the losses into count. If there are any questions about the above mentioned topics, please